Because Fourier series can handle piecewise functions or functions with jump discontinuity. Actually, that's one of the strong points of Fourier series. See, for Taylor series, you can only approximate functions that are differentiable infinitely many times, and with some more additional properties. It's that's called analytic. So you can only approximate functions that are analytic in order to have a Taylor series approximation. But for Fourier series, even if you have a function like f of x equal to 3x between 0 and 2, and then from 2 to 4, it's equal to x plus 1. Even if you have a function like this, you can still have a Fourier series. So let's try to figure this out. Let's say you want to find out Fourier cosine series. So let's think about the following question. Given this piecewise function, let's find out the Fourier cosine series. Now, these are just simply integration problems. The only difficulty is that now, when you integrate from 0 to 4, you actually have to cut the integration into 2, and you need one integral from 0 to 2, and then another integral from 2 to 4. That's what's needed. So 1 over 4, 0 to 4, actually 2 over 4, sorry. 2 over 4, 0 to 4, f of x times cosine of 0, that's just 1. This is the integral that you have to calculate. But because f of x has two different formulas from 0 to 2 and 2 to 4, you have to write this down as 1 from 0 to 2, where you use the formula 3, and then another from 2 to 4, where you use the formula x plus 1. And here, I just reduced 2 over 4 as 1/2, and I should really have said 1/2 times these two with the parentheses, but I just multiplied the 1/2 to each. So that's what you need. And integral of 3 is 3x. You have to plug in 2 and 0. Plus, integral of x plus 1 is 1/2 x squared plus x, and you have to plug in 4 and 2. Okay, let's see what that is. 6 divided by 2, that's 3. And then 4 squared is 16 divided by 2, that's 8. Plus 4, 12. 12 divided by 2 is 6. And then when you plug in 2, that's 4 over 2, which is 2. Plus 2, that's 4. Divided by 2, that's 2. And that's what you have to subtract. Right? So overall, that's equal to 7. So that's A0. Remember, the Fourier cosine series is f of x equal to A0 over 2 plus sigma n from 1 through infinity of an cosine n pi x over L. That's the Fourier cosine series, right? And for A0, we found out that that's 7. So we found out that this is 7. Right. Now let's try to do the same thing for AN. You have to calculate AN and A0 separately. Okay, AN equals to 2 over 4 again, 0 to 4, f of x cosine n pi x over 4 dx. Okay, that's the formula applied to AN. And again, we calculate in the same way. We split the integral into 2. 1/2 of one integral is from 0 to 2 of 3 cosine n pi x over 4 dx, and then plus 2 to 4 of x plus 1 cosine n pi x over 4 dx. Now let's integrate one by one. The first one, I guess, it's not that hard. You just when you integrate, you know that the reciprocal of this number should appear in front. So this is 3 times 4 over n pi sine n pi x over 4, and you plug in 2 and 0. That's the first integral. Now for the second integral, you need you have a question?
Yeah, real quick. Where do you get the 2 over 4 originally again?
Oh, the formula for an is an equals to 2 over L, 0 to L, f of x, cosine n pi x over L dx. And because the function is from 0 to 4, we are trying to take L as from 0 to 4. So the function is only defined on the right side, from 0 to 4. So our L is 4, and 2 is 0. That's where 2 over 4 comes from.
Thank you.
When you do it from 0 to 2, how come you don't make the L 2?
No, the function itself is from 0 to 4.
Okay.
If you do 0 to 2, then you're taking the Fourier series of this function only for 0 to 2. But so what I didn't say right here is find the Fourier series of this function over the interval 0 over 4. Find the Fourier cosine series of this function over the interval 0 to 4.
I know,
That's implied here.
but the 3, like, there's 2 different things, right? So I thought that the L for 3 would be 0 to 2, and the L for the x plus 1 would be 0 to 4. But I guess
No, that's not how it works. I mean, it's a single function. Don't think of this as 2 different functions. It's one function whose formula happens to be different for different integrals. So the formula, if you apply this formula here, it's 0 to 4 with L being 4, right?
Mm-hmm.
And that's it. That's what I get if I apply the formula. And then when I actually have to calculate this integral, then that's when you realize, oh, well, I have to split the integral into 2, from 0 to 2 and 2 to 4. And I really want these two to be equal. This equal sign means equal, right? For this integral to be same as this integral, you can't change suddenly from 4 to 2. That's not allowed. Okay? I mean, if the question was, find the Fourier cosine function of this function over the interval 0 to 2, then you would completely ignore this one and just find the Fourier series of this one from 0 to 2. So it'll be 2 over 2, 0 to 2, 3 cosine n pi x over 2 dx. But, I mean, why would you do that if the function is given up till 4? Make sense? Yes?
Mm-hmm.
Okay. All right. Now, so for the second one, we have to integrate by either tabular or integrate by parts. Let's use tabular. The integral plus minus x plus 1, 1 and 0. And then cosine n pi x over 4, 4 over n pi sine n pi x over 4. And then this squared, 16 over n squared pi squared, with a minus sign this time because if you integrate a sine, you get negative cosine. There's cosine n pi x over 4, and then plus minus plus. And using this, if you read what you have, it means you get plus x plus 1 times n 4 over n pi sine n pi x over 4. And then the next one is negative times negative is positive, so it's plus 16 n squared pi squared cosine n pi x over 4, and to this you have to plug in 4 and 2. The entire thing has to be divided by 2 afterwards. Okay? Now we have to plug in, and then this is where it gets complicated. Before, we were simply using the fact that sine n pi is 0 and cosine n pi is negative 1 to the nth power, and life was easy. Here it's not, because if you plug in 2, you get 2 over 4, which is 1/2, so you get sine of n pi over 2. So if you have sine of n pi over 2, when n is even, then you get multiples of pi, so you get 0, but if n is odd, you get some pi over 2, and in those places sine is either plus 1 or negative 1. So you actually have different answers depending on even or odd. Same thing over here. If you plug in 4, that's 0 because sine n pi is 0. If you plug in 4, that's cosine n pi, so you do have negative 1 to the nth power. But however, if you plug in 2, again you have that same problem. Sine n pi over 2 will be either positive or a negative 1. And over here, cosine n pi over 2, in that case it's the opposite. If it's even, you get positive 1 or negative 1, but if it's odd, you get 0. Okay? So you actually have to divide your answers into two cases. All right, so let's try this. When n is equal to 2m, if it's even, let's see what we get.
Why is it m?
M? I mean, how do you write even? What's an even number?
E.
What?
Can't do E.
Any multiple of 2?
Any multiple of 2, that's even number, right?
Capital
So
E.
I made it a multiple of 2. 2 times some number.
So m means positive?
M is some positive number.
2 capital E.
How would you write an odd number then?
2
2m minus 1, because if you have any even number, subtracting 1 off of an even number, you get an odd number.
It could be n plus 1.
You could write odd number as 2m plus 1, but if you do that, then m would start from 0, and I want m to start from 1. Alright? So if n is 2m, let's see what we get. We get 1/2. This entire thing will be 0 because, let's see, 3 times 4 over 2m pi, I replace n by 2m, sine of 2m pi, and then when you plug in 2, of course when you plug in 0, sine of 0 is 0, so we don't care. 2 times 2 is 4, so it cancels. So what do you get? Sine of m pi. What's that? 0, right? So the entire thing goes away because it's 0. So gone. Gone. Okay, for this one, again the same thing. If you plug in 4, it's 0. If you plug in 2, because n is 2m pi times 2, same phenomenon is exactly like this one will happen over there. So the second thing, this one will also vanish. So this, from this one, you're going to get a 0. And therefore, the only survivor will be this one. Let's see what that is. This is 16 over 4m squared pi squared. Right, because if n is 2m, n squared is 4m squared. That's where the 4 comes from. 2 squared is 4. Right? Okay, and then cosine of, when you plug in 4, you get 2m pi. Let me erase this one. And then minus, when you plug in 2, you're just going to get cosine m pi. Okay, so what's that? What's this one? What's cosine 2m pi?
Negative 1 to the n.
Negative 1 to the 2m. This is negative 1 to the 2n because instead of n, you have 2n, right? What is this?
0.
Negative 1 to the
N.
m, right? Okay, what's negative 1 to the 2n? If you take even powers of negative 1, what do you get?
0.
Positive 1, always. Always 1, right? Who said 0? So that's what you get. And therefore, we see that an, when n is equals to 2m, is 16 divided by 4 is 4, so let me just write 4. M squared pi, and then 1 minus negative 1 to the m. That's when n is equals to 2n.
Should it be pi squared?
Oh, I forgot pi squared, thank you. Alright, any questions so far? Yes.
Does it make a difference when you're stating the problem if the equal sign, you see how it says x equal less or equal than 2?
Okay. So
Does it make a difference where that equal
the
sign?
question is, would it make a difference if this equal sign was here or there? And the answer is because we're doing integration, moving one point doesn't make any difference. Okay. And that kind of raises the question: what do you mean by that? If you have a function which is a jump discontinuity, right? At jump discontinuity, Fourier series will converge to half of the jump. So regardless of whether you have the top one as the closed one or the bottom as the closed one, the approximated Fourier series will give you half of the jump value. So so in other words, even if you added infinitely many terms of the Fourier series terms, at the places where the function jumps, it wouldn't agree with the original function. So this equal sign has to be, this equal sign is not true for places where you have a jump discontinuity. But actually, I made this one so that it's continuous, although it should work. So mathematicians, when they talk about Fourier series, they say something like this is equal to that one almost everywhere. So that's the so they write something like a dot e dot almost everywhere. That's the way they say that. And if you ask me what almost everywhere means, that has something to do with measure theory, and it gets really complicated. But we're not going to go there. Okay. So going back, let's since we found out what this is for n equals to 2m, let's go after the case when we have n equals to 2m plus 2m minus 1. Okay. So if n is equals to 2n minus 1, let's see what happens. Now in that case, when you plug in 2 to this cosine 2n minus 1, this one will be 0. But signs will survive, because if you look at the graph of the sine, here's 2 pi over 2, 3 pi over 2. The sine graph goes like this, right? And it repeats over and over again, right? So what is sine of pi over 2? 1. What's sine of 3 pi over 2? Negative 1. Sine of 5 pi over 2? Positive 1 again, right? So if you have sine of 2m minus 1 over 2 pi, what is this equal to? Negative 1 to what power? Okay, should we do this? Will this work? When m is 1, what do you get? 1/2 pi. Sine 1/2 pi is negative 1. If m is 1. Does this work? Is sine pi over 2 negative 1? No, it doesn't work. So what should we do? put a minus in front, and then everything works, right? If m is 2, this will be positive 1. Negative 1 squared is positive 1, so you have negative 1 for m equals to 2. Let's see if that's true. 2 times 2 minus 1 is 3. 3 pi over 2. Sine 3 pi over 2, what's that? Negative 1, right? So it does work. You don't see it? If you follow, it does make sense.
Why'd you switch the n value though? You have to?
What do you mean? What's the question?
Nothing.
I handled the case for n equals to an even value, right?
Okay.
Now I have to handle the case for n equals to an odd value. Because this one is, I have to do this for n being 1, 2, 3, 4, 5, 6, 7. It's an infinite series, right? So n could be an odd number or an even number. So you can have a1, a2, a3, a4. For a2, it's handled by this one. For a3, it should be handled by this one with m equals to 2, and so on and so on. Why? Okay, so we have this following equality, and that's what we have to use, because when you plug in 2, 2 over 4 is 1/2, and you get exactly that. Okay? So let's see what happens. So that means you have an will be 1/2 of 3 times 4 is 12. 12 over n pi sine of, actually n is 2n minus 1, so 2n minus 1 pi sine of 2n minus 1 pi x over 4, and you're plugging in 2 and 0, right? So if you plug in 2, if you plug in 0, it's 0, so we don't care. If you plug in 2, these two cancel, giving you 1 and 2, and you see that it's exactly the same as this, right? So that means I can rewrite this one as negative of negative 1 to the nth power. So that's what you get from the first integral. Okay. From the second integral, if you plug in 4, that's 0, right? Sine n pi, that's 0. If you plug in 4 here, that's cosine n pi, so it's negative 1 to the nth power, but remember that's n is 2n minus 1, so you have to do 16 over 2n minus 1 squared, pi squared, times negative 1 to the 2n minus 1. But by the way, what's negative 1 to the odd power?
Negative 1.
Negative 1, right? So you don't have to put 2n minus 1 here. It's always odd. Okay? So that's what you get when you plug in 4. 4 plugged into here, it's 0. 4 plugged into here, it gives you this. Now let's plug in 2. If you plug in 2, cosine is 0 at odd multiples of pi over 2. So that goes away. When you plug in 2 here, that's when you plug in 2, that's 3. 3 times 4 is 12. So you have to subtract. So 12 over and 2n minus 1 pi, and then 12 over 2n minus 1 pi, and the sine of this much. This is what you're going to get when you plug in 2. So this is negative of negative 1 to the nth power. Okay, and it looks like these two are canceling each other, isn't it? See, negative of negative is plus, and this is a plus, but that's a minus, and they're exactly the same. So these two cancel each other. Okay, very conveniently. And this is what you get. Okay. All right, so how do you write down the final answer then? The final answer should be, the final answer should be in this format, in that format. So answer is the following. The above function can be written as f of x equals to 7 over 2 plus, now this time instead of saying n equals to 1 through infinity, we're going to say m equals to 1 through infinity. And for the let's write down the odd one first, because when you do 1, 2, 3, 4, 5, 6, the odd number appears first, right? So we're gonna say instead of a of n, we're gonna use this. That the final one. Actually, everything cancels, and this is the only thing that you have. And then 1/2 cancels that to make it 8 over. So you get negative 8 over 2m minus 1 squared, pi squared, attached to cosine n pi x over L, right? But what is n in this case? 2m minus 1 pi x over 4. And then that's how what happens for the odd numbers. For even numbers, we use this one. So plus 4 over n squared pi squared 1 minus negative 1 to the nth power of cosine 2m pi x over 4.
It's not m squared pi squared?
Oh, sorry, sir. M squared pi squared, yes. Okay, so make sure everything is in terms of m, and that's good. Okay, so that's the final answer. Now, of course, this is too much for an exam. So for the exam, I might just ask you what's A0, A1, A2, A3, or A4, about 5 terms. Those you can just use explicit numbers, so it'll be a lot easier.